Today, we are going to have a math history lesson because, in order to understand the new material that's coming up tomorrow, you're going to have a framework for where it's coming from and why this was even thought of. So, what I want to do is look at your calculator, and I've typed into my calculator the square root of negative 16. I hit enter, and immediately I get an error. And the reason why I get this error, think about what square root means. Square root means what number times itself gives you the number that's in parentheses. Well, I know the square root of 16 is 4. So if I look at 4 times 4, I'm going to get 16, which is positive, and I have a negative inside the square root. So maybe I'll just change it. Maybe I'll just do negative 4. So I'll look at negative 4 times negative 4, but I remember that negative times negative is also a positive, so I end up with positive 16. So no matter what number I use, if I multiply a number by itself, what I end up with is a positive and not a negative. So my calculator gets confused. My calculator just gives me an error. So this is an opportunity where you have to be smarter than your calculator. And let's see where all this came from. Let's go backwards in time just a little bit and do some math history. Since time began, man has had a need to count things. There's been a reason why he needs to know how many sheep he has, or how many ears of corn he has, or anything that can be counted. And so the numbers that he used to count things were called very creatively the counting numbers. So your counting numbers start with 1 because when you learned how to count as a little kid, you started with 1, 1, 2, 3, and the counting numbers go on and on forever. So I'll put a dot, dot, dot there to show it goes on and on forever. But it was very apparent very quickly that those were not enough numbers. You understand that at this point in history, these people thought 1, 2, 3, 4, 5, 6, 7 was all the numbers that they needed. As far as they were aware, that was enough. But it soon became apparent that that was not enough. Sometimes you had none. Marauders came during the night and took your sheep. The sun was too hot and you got no corn. So there became a reason to use 0 as a number. And once we do that, we enlarge the counting numbers and we call it the whole number. So the whole numbers, if you remember the way Venn diagrams work, the whole numbers include all of the counting numbers and then also the number 0. The 0 is the only whole number that's not a counting number. It's the only one we need to add in there. Well, the idea of 0 came up with two different civilizations, the Mayans in the Western Hemisphere and the Babylonians on the other side of the world. Both of them came up with a numerical approximation or a numerical way of showing 0. Neither the Greeks nor the Romans, for all of their advancements, had a number that represented 0. They certainly had a concept of 0. They can say, I have no sheep or I have no grains of corn, but they didn't have a number that meant that. So the Mayans and the Babylonians are credited with that. So again, at this point, we thought we had all the numbers that we needed, but we didn't. So as time progressed, as people thought more and more about mathematics, they realized that sometimes you owe somebody something, or sometimes you have less than nothing for some reason. And so we needed to increase from the whole numbers, and now we have the integers. So again, thinking about Venn diagrams, the integers include all the counting numbers because this circle is inside this circle. It includes the whole numbers, includes 0 because that circle is inside this circle, but it's going to add on to this the negative. So -3, -2, -1, and this time I'll put my dot, dot, dot on this side because the negative numbers go on and on forever in that direction. So Brahmagupta, who was an Indian mathematician in the 600s, he had an idea of negative numbers. Also in China, 800 years before that, in the 200s BC, they had a way of demonstrating negative numbers. So negative numbers were used in various parts of the world. In Europe, it was many, many centuries later before they came up with, or they agreed to use negative numbers as part of their mathematics. Okay, so in addition to integers, it doesn't take long to realize that if I draw out a number line, there are spaces in between -3 and -2. There's a space in between +3 and +4, and that space is filled with something numeric. So both the Egyptians and the Arabs had an idea of fractions, Here's an Egyptian fraction. Unfortunately, the Egyptian fractions were very difficult to work with. You could only use unit fractions. The Arab fractions were a little bit more like what we see today. The Hindu people actually came up with some of these ideas, and the Arabs were the ones that added the fraction bar. In Europe, in addition to fractions, they worked on decimals. You can see here kind of a history of how the decimal point came to be like what it is now, starting with the 1500s and moving forwards. And here's what it looks like now. So these numbers, if I add in the fractions and I add in the decimals, now I have rational numbers. So rational numbers can include any fraction, but they only include certain decimals. They include decimals that terminate, like zero point 0.7, it comes to an end, zero point 0.7, and then you're done. And it also includes decimals that repeat, like 2.7 with a bar over it. So now I have my rational numbers. So again, think about Venn diagrams. Rational numbers include these numbers, the fractions, and the decimals that either terminate or repeat. But rational numbers also include all of our integers because the integer circle is inside of the rational circle. So -2 is a rational number that happens to be an integer. 0.7 is a rational number that is not an integer. This 0.7 is in the rational circle but not in the integer circle. -2 is in the integer circle, which automatically makes it inside the rational circle as well. And same thing up here with +3. +3 is a rational number that happens to be an integer, and it happens to be a whole number, and it happens to be a counting number. But 3/5 is a rational number that is not an integer or a counting number or a whole number because it's outside of those circles. Okay, but we realize again that that's not all of our numbers. We still have more numbers. Hippasus, a Greek mathematician in the 15th century, was the first one to realize that we have other numbers, numbers like square root of 2 or like pi. Those kind of numbers are not rational. If you remember when you learned about pi in the past, pi is a number that goes on and on forever with no repeats and never ends. Same thing for square root of 2. Goes on and on forever with no repeats. It never ends. These kind of numbers are what we call irrational numbers. And if we put the irrational numbers and the rational numbers together, what we have are all of the real numbers. Okay, so real numbers include irrational numbers like square root of 2 and pi. Real numbers also include rational numbers. So if we take the rational numbers and the irrational numbers, combine them, what we get is the real numbers. But again, that's not sufficient. It's just that that's as far as you have gotten at this point in your mathematical career. But starting today, we're going to step outside of the real numbers and we're going to learn about something new. So a couple of Italian men who actually were not mathematicians, they were munitions experts. And as they were looking at shooting their weapons, a weapon shooting often makes an arc path. Let me draw that for you right here, right? What does that look like? Well, it looks like a parabola, like the purple one that I have here. And what they noticed in their calculations for how to shoot things, or they would have mathematical battles at this point with different theorems and different algorithms. And what they noticed was there were some parabolas like this one, which cannot be solved using the numbers that we have. So if I take that, x squared plus 1 equals 0. Suppose I want to try to use the zero product property and figure out what x is going to be. Or maybe I want to try using square roots. I notice that this is a sum of squares, so it doesn't factor. So I'm going to try square roots. So I'm going to subtract 1 from both sides, working to get x squared by itself. Well, then I have to take the square root of both sides, and I remember when I take the square root, I need to write plus and minus. Well, what I end up with plus and minus the square root of -1. And what these men soon realized was that this was a number that they could work with. They could actually do calculations with this number, but they couldn't write it using any of the mathematics that we already knew. So another Italian mathematician, Bombelli, ended up writing out what this number was and how to work with it. He actually wrote a textbook for people who were not mathematicians so they could understand what this number was and how to use it. And the notation that we have is I. So the number I, by definition, is the square root of -1. So just like when you learned about pi, you learned that pi is a number and pi is approximated by 3.14, but it goes on forever. And every time you see pi, it's that same thing. It doesn't matter if you see pi in a circle or in a cylinder or in a ball, pi is always 3.14 on and on and on and on forever. And it's the same thing with I. I, by definition, is square root of negative 1. And it doesn't matter where you see it, in what context. I is always the square root of negative 1. So what we have is the square root of 9, which you have already learned in your past. The square root of 9 you know to be 3, because 3 times 3 is 9. But if we have the square root of negative 9, okay, think about that. Negative 9 is the same thing as negative 1 times 9. Well, I already know the square root of 9 is 3, and I'm learning today that the square root of negative 1 is I. So the square root of negative 9 is 3I. All right, let's look at what that means. We are going to be learning about complex numbers. Complex numbers have two parts, a real part that's called A and an imaginary part which is called BI. So a complex number is generally written as A plus BI, the real part plus the imaginary part. So here's an example of a complex number. The real part would be the 4 that's in the front. That's what you're used to. You've been working with real numbers since you were very, very small. The new part, the imaginary part, is here, and I recognize it because it has that I on it. So 4 plus 5I would be an example of a complex number. And here's how those work. So square root of 25, you learned how to do that several years ago. The square root of 25, what number times itself is equal to 25? Well, that would be 5. And if I put a negative on the outside of my square root, that's the same thing as saying like negative 1 times the square root of 25. Well, the square root of 25 I already know to be 5. Negative 1 times 5 is negative 5. So if you want to think about it, that negative on the outside just stays on the outside, and the square root of 25 is 5. And that works for any square root you could possibly come up with. The negative that's on the outside just stays on the outside. But today we're learning what happens when I have a negative on the inside. So when I have a negative on the inside, I know positive 5 times positive 5 is positive 25. Negative 5 times negative 5 is also positive 25. And if I want something times itself to equal negative 25, that something is going to have an I in it. It's going to be an imaginary number. So 5I times 5I equals negative 25. The square root of negative 25 is 5I. And I don't want you to get the impression that I imaginary means imaginary like leprechauns and unicorns. I, in this case, was a way of expressing something that was just outside of the real numbers that we already had. If all these other numbers are called real numbers and this new number doesn't fit in that category, I have to have a new name for it. The opposite of real is imaginary. So it just means imaginary not fitting into the real number system, not imaginary like it doesn't actually exist. Imaginary numbers actually have lots of uses: theoretical physics, electrical engineering, all sorts of reasons why you might need to use imaginary numbers in your future. But what we're going to be learning about in this next section is how to simplify and how to work with those imaginary numbers, because just like our Italian munitions experts, we are going to be solving quadratics that sometimes don't have a real solution, and we need another way to write that solution down so that it makes sense mathematically.